So my project title is What is the optimum climate for the highest quality of sound in live music? The idea came about after doing some work experience with Vanguardia last summer. We were told that as the air cools in the evening, there would be more likely to have noise complaints. I found this concept quite intriguing, so began to research temperature gradients causing refraction. Many articles said that temperature affected sound, but it didn't say why or to what extent. So I decided to dig deeper, resulting in the original title of Optimum Temperature for Best Sound. I discovered that while temperature does have a marginal yet also considerable effect on sound, there were other factors as well, such as air humidity and density. So I decided to change my title to encompass all of these. Throughout the project, I looked at how climate factors contributed to altering a sound wave. I was able to establish an ideal temperature and humidity percentage to optimize sound propagation, meaning that I answered my question. However, the numbers were based on secondary research, and the acoustics of the venue itself would have had a big effect on top of the climate. So while I did come to a conclusion, it wasn't backed up by primary data as planned, and there were a lot of open-ended what-ifs. I did complete my aims, but not all of the objectives were met due to access restrictions because of the epidemic. Though on a positive note, I now have a more in-depth understanding of sound in different climates, which was the main goal of the project. The part I found most interesting was thinking about factors other than temperature, such as wind and haze machines. Wind is determined by temperature differences, but I treated it as its own factor under the umbrella of temperature. I knew that sound travelling in the same direction as the wind is carried further, but I learned that it only has an effect over 50 meters, and that wind gradients are also a cause of refraction. And with atmospheric, such as dry ice, I knew the density was far greater than that of air, hence why it sits on the floor of the stage. But I had never pieced together about refraction gradients as the sound passes through the different densities. Though despite all the talking of refraction gradients, their effect appeared to be actually quite small, unnoticeable to a human ear. I had planned to do frequency response and SBL tests with different temperatures, humidities, and air qualities to firsthand see the effects, but unfortunately I didn't get a chance to. The part I struggled with most in the project was finding useful sources. There were many articles about sound waves, factors affecting them, speed and mediums, but most did not go into the desired depth and explain why those effects happened. I had to trawl through many websites, journals, and books to find maybe just one sentence that backed up what I was writing, and even then, sources would contradict each other. I was getting easily confused between concepts such as the difference between humidity and density of air, and how sound behaved as these changed, because they were two very closely related factors. I found the solution was to break factors down and read simpler texts, such as GCSE definitions, and then build my understanding up from there.